Hi, everyone. Thanks for joining us at the National Solar Observatory. I'm Tishana, and we're here doing our Learn from Home webinar series. And so today's featured scientist is Dr. Claire Raftery. She's a solar physicist and science educator originally from Ireland. Having researched solar flares and coronal mass ejections, she's now Director of Education and Outreach and Communications for the National Solar Observatory, which is the organization responsible for building the NSF's Inno Solar Telescope. And an extra bonus is that Claire loves telling science stories, which got her into education. So without further ado, here she is now, Dr. Claire Raftery with If It's Not Caramel Corn, What Is It?
Thank you, Tishana, and welcome everybody, and thank you for joining us today. I'm excited to talk to you about what it is that we see when we look at the sun, and hopefully you'll be able to follow us on this journey. This webinar will be recorded and you'll be able to watch it at a later date also if you wish. So when the Inno Solar Telescope released its first images online earlier this year, we had a whole series of guesses at what it looks like, and caramel corn was one of the most popular. So we're gonna discuss that a little bit today. But first of all, I would like to give a very special shout out to Catherine Lempesi, who was an intern at the National Solar Observatory this year, and she helped to put together this presentation. So thank you, Catherine. So the first pictures that came from the Inno Solar Telescope show boiling, roiling, liquid plasma gold almost on the surface of the sun. And people see all different kinds of things when they look at this picture. So first of all, I want to take a minute and have you go to the comment section on YouTube and tell me what you see when you see this picture. So type into the comment section what you see when you look at this picture, the boiling, bubbling, plasma, liquid gold type thing. I know when I see this picture, I see things like fish scales. I see honeycomb, like the candy bar. Caramel corn definitely jumps to mind. There's all different kinds of things that show up here. So before we get into the details of what we're seeing with this picture, I want to take a minute to discuss the context for it, just to put everything in context first. So this picture right here is a picture of the full disk of our sun, and it was taken with the NSF's GONG network, which is also run by the National Solar Observatory, which is the institute that I work for. So this is the full disk of the sun, and you can see some prominences sort of sticking off the edge of the sun, and the same here. But overall, you can see it's a pretty quiet sun. We don't see any major sunspots or anything like that going on. This was at the depth of solar minimum. It was actually taken at what we think was the very lowest point of solar activity during this solar cycle. And then in the center of this picture, you can see there's another image that's overlaid on it. And this is the picture from the Inno Solar Telescope. And this actually is as much of the sun as the Inno Solar Telescope can see at any given time. It can only see a snapshot of the sun, and in order to see multiple areas of the sun, we have to move the entire telescope and camera system around to be able to capture that. But the benefit of this telescope is that it can see the sun in super duper detail. This is the highest resolution or the most detailed picture of the sun that we have ever seen before. So you can see this picture here, that it's blown up quite big, and it's actually only even a smaller subsection of the surface of the sun right here. So this picture, for context, is 7,000 kilometers by 7,000 kilometers, or almost 4,500 square miles. And this is, as I said, the highest resolution picture of the sun surface that has ever been taken in the history of mankind. This is the most powerful solar telescope in the world, and because we assume there are not many other alien species looking at our sun, we can extrapolate to say that it is the highest resolution picture in the universe, perhaps. And what does that mean? Well, it means that one of these blobs, we call these granules, solar granules, and we'll explain these in just a few minutes, that one of these is about the size of the entire state of Texas. So that's, again, context of the kind of size scale that we're dealing with. And then down here, the smallest details that we can see are still about the size of the island of Manhattan in New York City. So it's still pretty massive. Or another way to compare it would be the island of Molokai in Hawaii. So these scales, even though they look infinitesimally small on these pictures, are still really, really massive. So let's put them to scale. So if we took the island of Manhattan, as we saw in that last picture, it's about 25 kilometers across, or about 13 miles across. And so if we put this back in context on the planet Earth, you'd see that it would sink nicely into the east coast of the United States. And if we take the entire planet and put it in scale of the solar system, then the sun being 150 million kilometers away, the Earth is really, really tiny. You can only barely see it anymore over here on the right-hand side. So think about that island of Manhattan and just how small it was and how he shrunk it even smaller and pushed it further away. So instead of thinking about us looking at the sun from the Earth, if you turn it around and think if we were sitting at the sun, looking at the island of Manhattan, how tiny that would be so very far away. So this was a really big deal. This is many times smaller than anything we've ever been able to see on the sun before. So these pictures really had scientists scrambling to explain them, because there was observations and there was features showing up in these pictures that we had literally never seen before, because we've never had a telescope able to resolve them this well before. So these features, these little bright points in between here, these are the size of Manhattan or Molokai Island, these tiny little bright spots. But think about that from the overall scale of the sun. But what are they? What is it that we're seeing? So we see all this boiling, moving mess of stuff. What is that actually showing us? Well, if we compare these three pictures, we have three entirely different setups here. On the left, we have a bowl of miso soup. So the next time you get miso soup, perhaps not in a restaurant anytime soon, but the next time you're eating miso soup, before you eat it, pause for a moment and watch it as it settles. Give it a bit of a mix and then let it settle. And you'll start to see that it sort of has this really interesting pattern that happens. The picture in the middle we have there is the picture of the surface of our sun. This is the one we were just looking at earlier. And then on the right-hand side here, we have a video of a concoction of regular vegetable oil and some special glitter, mica powder actually, that's sitting on a hot plate, a hot pan. And we can see similar kinds of patterns. So what is it that we're seeing in this? If you know, jump into the comments and tell us what it is that's causing these three different types of patterns to appear, and what they might have in common. So Tishana, if there's any responses in the chat, let me know and we can read them out perhaps. Jumped the gun on this one and I let the cat out of the bag.
No problem. Yeah, no comments yet.
Okay, so the answer to this is that they all show convection. These are all showing convection patterns. And this is the mechanism, one of three mechanisms by which heat is transferred. So heat is being transferred, in this case, from the liquid between liquids and solids, liquids and gases. And so the convection patterns that we see start to show up here is as material is heated low down, it starts to rise up. And as it reaches the top of the surface, it loses its heat and it falls back down again, and it creates this sort of bubbling pattern. And so I'm sorry, go ahead.
Brad Denny asked if this is thermal distribution. So is this another way that heat is distributed?
Yeah, that's a good way of thinking of it. So the heat is being distributed through the system. There we go, we get these playing again. The heat is being distributed through the system. In the case of the oil and the miso soup, into the air, the local air. It's being distributed from that interface between the oil or the liquid and up into the atmosphere nearby. In the case of the sun, it's from the surface of the sun into the chromosphere, the lower area of the sun's atmosphere. And we'll actually delve into that a little bit more in just a few minutes. That was a great question. Thank you. Okay, so let's keep going here. So where else might we see convection? Where else, especially on the planet Earth, is convection a big deal? So again, jump into the comments and see if you can think of any places on the Earth that you may recognize convection. I'll give you a hint that some of it is a very large body of liquid that covers most of the planet. Any comments yet?
Brad Denis says waves.
Waves, almost, yeah. So we see convection in oceans. So the ocean has these very large convection patterns. And so that's a big deal for us on the planet Earth. And this is a great demonstration of the process of convection. So I want to give full credit to the Singing Zoologist on their YouTube channel. This is adapted from their YouTube, and so I appreciate this being available. So this demonstration starts with a plastic container with some food coloring just over a cup of hot water. And so this white cup down here is providing the heat. And as it heats the water near to the surface of the cup, you can see the food coloring getting mixed up with it. And so the water is rising to the top of the surface, where it starts to lose some of its heat to the air nearby. And as that happens, it starts to sink back down again. But in the meantime, more water is being pushed up behind it. So this stuff is getting pushed out of the way. And you set up this sort of circular pattern going round and round in these big convection cells, or granulation cells as we call them on the sun. So this shows really nicely this process of convection. And this is the very same thing that we see happening on the surface of the sun. And it actually starts inside of the sun. It starts lower down from beneath the surface. We will explore that now. So this is a cartoon graphic of what the sun looks like. And if we start inside, we have the core of the sun, which is this bright area right here. And this is where solar energy is created by nuclear fusion. This inside here is where the energy produced by the sun is created. And then the energy passes from the core through this area here where you can see the stripes. This is called the radiation zone. And actually the stripes are a bit misleading because that suggests that the energy is able to travel in a straight line. In actual fact, that the energy takes so long to leave this, to get from the core of the sun to the next layer out, it takes a million years or so for the energy to be able to make this journey. And that's because this area of the sun is so very dense that every time a light particle travels just a small distance, it bumps into another particle and it gets kind of elbowed out of the way. And so instead of traveling in a straight line, it has to scatter in what we call a random walk, and it goes all over the inside of the sun. So it can take a million years or so for a light particle to go from the core out to the next layer. And this next layer is the convection zone. So this is what we've been talking about so far. So you can see these looping circular patterns. Now this is an artist's representation, of course, but this is what we're trying to show here, is that the heat is traveling from the edge of the radiation zone right here out towards the surface of the sun, where it loses some of its heat and it falls back down again. And then it gets heated back up and it comes back to the surface and back down. And this is when we see the top of these as granulation cells. And that's what we see in this picture from the Inno Solar Telescope. So if we think back to that previous slide, or the previous movie with the food coloring, the blue and red food coloring, if we were looking down on the top of that, then we would be able to see a very similar pattern to what we see with these granulation cells on the sun. So we're looking at the top of that on the sun, as opposed to side on in that movie from the Singing Zoologist. So this is definitely not to scale. I have just stretched this movie to be able to see roughly what it would look like. This is, we saw earlier that this video is only a very small size of the center of the sun. So I've stretched it out to be able to fill this area. So in addition to the solar surface, another interesting area of the solar atmosphere is called the corona. And no, I don't mean the virus. The corona is this area out here. It's this sort of faint, fuzzy, sort of structured but not structured, very strange sort of area that normally we don't see unless we have a total solar eclipse, which happens quite infrequently, about every 18 months or so. But we have specialized instruments that are able to show us what the corona looks like. So this picture actually was taken during a solar eclipse. It's two pictures pasted together. So this outside picture of the red and the green is courtesy of Dr. Shadia Habal, taken during a solar eclipse. And this picture on the inside, this gray and black and white picture, was taken by one of NSO's gong imagers again. And it is a graphic showing the magnetic field map of the sun, because the sun, the reason we have all of this structure in the outside layers of the sun is because the sun, in fact, is magnetic. It shows all of this structure to be as a result of magnetism, much the same as we have with a bar magnet. So in middle school, perhaps, you may have played with bar magnets and iron filings, where if you sprinkle the iron filings over a magnet, you see that it produces sort of a butterfly shape. And this is very similar. So we see these sort of straight lines coming out at the top, and then we see the looping structure going from one pole to the other pole. Now, of course, there's all of this noisy stuff here, which we'll talk about in just a second, but the main structure of the sun is this magnetic north-south structure here, where we have this looping stuff go around the outside. But these things here, these loops right here, these are called coronal loops, and they often sit over active regions, or sunspots as they're also called. And this is as a result of the sun's magnetic field bursting out through the surface in what we call sunspots, and that's what you may see here. So if we were able to put pictures of the sunspot on the edge here, if we were able to see them, then you'd likely see sunspots also aligned with the what we call the foot points, or the places where the sun's magnetic field reaches the surface of the sun and then loops back around on itself. And so these loops that we see here are the sources of a lot of solar activity. It's where we see solar flares and coronal mass ejections coming from, and a lot of that eruptive dynamic behavior that the sun is known for, or maybe not known for. So as I said, magnetism is the reason for much of the sun's explosions. And one of the cool things about the Inno Solar Telescope is that it's going to have a dedicated instrument that will focus on studying the sun's corona. It will also be able to study parts of the sun's surface, but it's going to be really unique in that it's going to be able to study the magnetic field specifically in this area of the sun's corona when we don't have a solar eclipse. So that's very hard to do normally, especially this area very close to the sun. When we have instruments that are in space, usually we have to block out this part of the sun so as we don't accidentally overexpose our cameras, because the sun is so bright compared to the faint corona out here. And so if we accidentally expose the cameras to the bright sun, then we'll just cause them to bleed, and they won't be able to see properly the rest of the corona. And so the Inno Solar Telescope will be really useful in being able to tackle some of that. So here's another show and tell. Again, if you'd like to jump into the comments and tell me what it is that you see here. So in this picture, this was taken by the NOAA GOES 16 satellite, the SUVI instrument, and thanks to Dan Seaton for giving me access to these movies. And so you can see some of these loops that we saw on the edge of the sun in the previous slide, but we can actually see them on the surface of the sun, or sort of on the surface of the sun with this one. And we can see an explosion happening out here. So the bright stuff, this loop with the bright lights showing up, this is called a solar flare. So a flare is light and energy. And then the explosion of stuff, of material and magnetic field, that's called a coronal mass ejection. So these two things often go hand in hand, although they are two different sides to the same coin. So do we have any comments on what people are seeing in this picture?
We have a Facebook comment actually from Craig Merriam. He says metallic liquid hydrogen.
That
So,
is, yeah, it looks like that, doesn't it? I don't even know what metallic liquid hydrogen would entail, but it certainly sounds like it would fit the bill here. So in this picture, the main thing I wanted you to notice was this big explosion, this coronal mass ejection that goes off in the corner. And then in this picture, it's ever so slightly different. So again, if you want to point out what you see in this picture, this I think is really impressive. This is also from the GOES 16 satellite and courtesy of Dan Seaton. And I think that there's lots of different things going on in this picture. So we see many loops, so that we see a nice big coronal loop here, and then we see some sort of thing going off. And what else are we seeing in this picture?
we have one from Gerard Oribe, plasma ejection, protons, X-rays, and kind regards from Mexico.
Oh, well, thank you for joining us from Mexico. We're really happy to have you here. So yeah, you're certainly onto things. The sun, this whole system is made of plasma, so you're spot on there. And when we get a large eruption like this, this is our solar flare. We do get X-rays. We get high energy X-rays and we get lower energy X-rays called hard and soft X-rays respectively. And they tell us about where energy is being deposited in the solar atmosphere. And so when we get hard X-rays, or the higher energy end of the X-ray spectrum, then we know that there's a lot of particle acceleration going on, and often that is connected to protons. So yeah, you really, you're spot on with that. The other thing that I want to point out with this particular video is after we get this eruption, watch the actual surface of the sun over here, and you should be able to see a wave that moves across the entire surface. So here it goes. And you can see it move across the whole surface of the sun. So just pause for a second and think back to the scale that we discussed earlier. So we were looking at a picture that was about the size of maybe one of these sunspots, and then we were looking at detail much, much smaller than that, and that was still the size of the state of Texas. So can you imagine how much energy it would take to produce a wave that would cover the entire surface of the sun? You could fit 109 planet Earth side by side across this distance. So how much energy must this take to be able to move a wave across the whole surface of the sun?
And Brad Denny asks, how large can the ejections be?
That's a depending on the many different factors question. So size, the size of coronal mass ejections, physically, they generally increase as they move away from the sun. So they start small, and as they move away from the sun, they sort of expand. And you can kind of see that in this picture here. If I move it back a little bit to about here, let me see here. So you can see that it starts small, and then as it gets bigger, as it moves forward, oh, it's not going to let me do this. We'll let it play. You can see that it sort of goes and it expands outwards. So they get to be, you know, I don't even know if I'd be able to guess at the height, the vertical scale of these things, but many, many thousands of kilometers, probably even tens of thousands of kilometers. And then the energy of these depends on the size of the eruption and the size of the flare attached to them, the particle acceleration, but they vary enormously depending on the size of the loop that's exploding for the most part. So you can get micro flares, which you can actually see a few micro flares popping up. They're tiny little bright spots that show up over the sun. You can see one sort of coming on over here, and then you get these larger flares. The largest solar flares that we get, we classify them as X class. They are A, B, C, M, and X are the increasing size. So an A flare is teeny tiny, and an X flare is some of the biggest that we get. And so generally at the height of solar maximum and in the declining phase towards solar minimum, we get some of the biggest solar flares. So this video was from 2017, which is about halfway through the solar the decline from solar maximum to solar minimum in the last solar cycle. And we had a flurry of solar flares in September of that year that were all really, really big as a result of a huge sunspot that are worth Googling if you are so inclined. So we're sort of dawning into a new era of solar observations. It's a really exciting time to be a solar physicist. I've mentioned the NSF's Inno Solar Telescope, and you may have also heard of NASA's Parker Solar Probe and also the ESA NASA Solar Orbiter. So Solar Probe was launched in 2018 and the Solar Orbiter was launched earlier this year in February. And so these three missions together are going to really transform how we study the sun because of the way they do it. So Parker Solar Probe and Solar Orbiter are leaving the Earth and they're actually going to travel towards the sun. Parker Solar Probe is already quite near to the sun, and Solar Orbiter has started its journey in that direction. Solar Probe is going to ultimately get much closer to the sun. I think it's going to come within 10% of the distance, so almost the entire way to the sun. And Solar Orbiter won't get quite so far, but the instruments that they have on Solar Orbiter can cover sort of a wider range. They have some imagers on there and so on. So if you think of the Inno Solar Telescope at Earth and the Parker Solar Probe almost at the sun as the bookends, and then Solar Orbiter is like a hybrid of both. And all together, these three instruments are going to help us capture data from the sun like we've never done before. So for example, the satellites are going to be able to go, as they go on their path, to directly measure the magnetic field, the particles, the stuff that's in situ, we call it nearby to where they are, whereas the Inno Solar Telescope will be doing remote observations from the Earth looking towards the sun to give that bigger picture context of where the magnetic fields are starting from and what it is that the probes are going to be flying through. Do we have a question?
Yeah, we have some great responses here. So the first is about the sun. Once it dispels the energy, is it heat or light?
Oh, it's both. So the heat is, this is the infrared debate, right? So the heat is a form of light, and so as the photons travel from the sun, they are carrying with them energy that ultimately, when transferred, becomes heat. It increases the temperature of something else. And so this can happen, in our case, it generally is something that we might notice in the Earth's atmosphere. Now, it happens so little that it's not something that's noticeable. It's a pretty constant stream. And the light is transferred also in a similar way, where the energy from the light is, I mean, the energy from heat and light is the same thing. And so they get transferred into the Earth's atmosphere and they cause, actually, that's how the aurora happens, is that the energy from the light coming from the sun gets transferred into the Earth's atmosphere, and it causes the particles in the Earth's atmosphere to glow because they have all this extra energy all of a sudden. So they're able to sort of do a little happy dance, and they shine different colors, green and red and purple, depending on which atom in the atmosphere is being excited at the time.
We also have Alex from 2019 REU here, and he's joining
Hi, Alex.
his lunch. He wants to know, Claire, what are you looking forward to in the next few years with solar research? And will the 2024 eclipse be interesting since we will be in maximum?
I'm going to hold off on that question until we're finished, if that's okay, because I still have a few more slides to go, and maybe we'll come back to the question at the end.
Okay, did you want to do an energy particle question before going forward?
Sure, since we were talking about that,
yeah. Okay, so Gerardo Ribe asks, is it possible to store these energy particles to use in satellite systems instead of solar panels? Photons versus electrons.
So you mean capturing electrons to use instead of capturing photons for solar panels? Presume that that's what you mean. I actually don't know. That's a good question. My assumption is, well, if you're in space, I don't know what the conditions might be. So solar panels work by capturing photons. They use photons to excite the materials in solar panels, which then go on to produce electricity, which is ultimately a flow of electrons. I think the biggest issue with capturing electrons instead of photons is when you have access to them. So the way in which you can capture electrons and photons will be quite different. So I don't know enough about the electrons question to be able to give you a straight answer, but I know with the photons that is how solar panels work, and it works pretty efficiently. I know that there's some studies at the moment to consider solar sails, which instead of capturing electrons or doing something like that, the way it works is it uses pressure from the sun and the solar wind to almost like a sail on a sailboat, where you use the Earth's wind to push it along. That they're doing some test runs on solar sails, I think, in the next few years. So you should watch this space to see if any of them are successful. So that's kind of an exciting progression in technology these days. Okay, so I'm going to keep going for now, and then we can take more of your questions towards the end. So of our three new missions that I mentioned, I've already mentioned the Inno Solar Telescope a little bit. We saw the first pictures that came from this telescope earlier this year. This telescope is almost finished construction in Maui, Hawaii. It's on the mountain of Haleakala, and it is a 4-meter class solar telescope. So 4 meters is about 13 feet. And from a nighttime perspective, that's not very large. But from a solar perspective, from a daytime astronomy perspective, this is the largest solar telescope that has ever been built. So for context, this is 4 meters, and the next largest solar telescope that we know of is, I think, 1.8 meters. So that's how big of a jump we're going with this telescope. It was scheduled to start operations during this summer of 2020, but unfortunately the pandemic delayed construction. So we're hoping that will be ready for regular operations early next year. So in the spring, perhaps, of next year. That's obviously a moving target depending on how things progress with the pandemic and so on. But we're keeping our fingers crossed. And you should watch this space for some new pictures of this coming from this telescope in the near future. It's all very exciting. So the inside of this telescope is really quite, it's quite complex, but we're going to have a go at walking through it. So up here we have the entrance aperture. This is basically the hole in the dome that allows the light from the sun to shine through. And the light comes through and it hits this mirror right here. This is our 4-meter mirror. This is the record-breaking mirror. 4 meters, as I said, is about 13 feet. So you can think about just how big that is. I have a span of about 6 feet, and so 2 of me side by side is how big this mirror is. And I have some pictures of it in just a moment. The light comes in and it bounces off this primary mirror. And then, unlike a nighttime telescope or many other telescopes, it goes off at an angle into this area here. So the reason that we have it go at an angle is that we want to be able to study some of the faintest and most detailed objects on the sun, things like the corona and the small scale magnetic field. And in order to be able to do that, we have to preserve the beam of light as much as we possibly can. So normally a telescope would work by having the light come in, and up here there would be a secondary mirror. So the light would bounce straight back off and go back to the secondary mirror up here. But by doing that, we have to use what's called a spider, which is basically like a strut to hold the secondary telescope up. And those struts cause scattered light, and we can't afford any of that scattered light because the stuff we want to see is so small scale and requires such high detail. So instead of bouncing it straight back up, we go to the extra effort of bouncing it to the side. So this concept is called an off-axis telescope. So right up here, we have what's called a heat stop. And this is essentially like a donut that allows the light to pass through, and it absorbs a lot of extra heat. And the extra heat is really important, because if you can just imagine for a moment that you had, perhaps you played with magnifying glass when you were younger, and you had a magnifying glass and you were able to burn paper or something like that with it. You can imagine if your magnifying glass was 13 feet across, just how much energy and how much heat would be collected by that. And so the heat is gathered and transported away from the telescope at this point here. So we have 7 miles of piping dedicated to piping coolant throughout the entire system. And that is a really important part of this whole system, because not only do we need to keep the temperature cooled for safety purposes, but we need to keep it super stable as well, because otherwise we end up with aberrations, a bit like a mirage in a road on a hot day. And if we get that, then it means that we are going to see that in our images, and that defeats the purpose of building such a high resolution telescope.
We have a quick temperature question.
Sure.
What can you say the temperature would be if not for the coolant?
Oh, I actually don't know. I wish I could tell you. I will say that we have another Learn from Home webinar called if Decist could pop popcorn, that you should go and take a look at, where one of our scientists goes through and does a sort of a thought experiment on how much time and energy it takes for Decist to pop a bowl of popcorn if you were able to put the kernels in the beam of light of the telescope. And so Sarah Yeagley, one of our scientists, may have mentioned the exact temperature, but I can't remember what that is off the top of my head.
Xander says he thinks he's seen photos of melted steel from the Big Bear Solar Telescope. So it gets hot.
Quite possibly. I know that when the very first time they turned the Decist Solar Telescope on, there was some smoke coming off some of the instruments because there was a tiny little bit of residual glue that was in the way. Luckily, it was all very safe and above board, but that certainly, I'm sure, made for some scary moments with the rest of the team. So once our light goes through the heat stop up here, we have a secondary mirror. So this is another mirror that lives up in this box, and it guides the light down through another series of mirrors right here. Oh, whoops, too fast. I've got a preview of all of my slides. I should not use my mouse. There we go. And it guides the light down through the telescope into this area right here. And this is a very special part of the Inno Solar Telescope. So often with research telescopes, up here, right here on the back of the telescope, you'll put your instruments. So they sort of dangle from the back of the actual telescope. But that's not how this instrument works. The light gets guided down through the telescope and onto a platform called the Coude Lab. And this platform, the instrument laboratory right here, this actually rotates during the day. So the whole platform, many tons, rotates very gradually as the sun rotates in the sky. And the reason we have to do this is as the sun passes across the sky, it appears to rotate. So what is pointing upwards at one part of the day will then start to rotate around and be pointing in a different direction later in the day. And again, if you're building a telescope to get the highest resolution pictures of the sun, then having it smear across the sky is not going to be very useful. So in order to compensate for that rotation, we move the entire instrument system beneath it in order to compensate. So when the light comes down here into this area, the light gets fed into up to 4 different instruments at one time. So we have 5 instruments in this area, and up to 4 of them can work at the same time. And you can see in here, this room is our control room, and this is where our instrument operators will sit. These are specially trained technicians and scientists who are designed to control and operate the telescope. So they send all of the commands to the telescope, where to point, which instruments to use, and they also make sure that everything is nice and safe and under control. And that's why they're in this separate room, because there's a lot of energy bouncing around this room, and so we want to make sure that they stay safe. So here's some videos of the actual telescope. This is the top part of the telescope where we have the primary and secondary mirror. And this is actually in the lab where it was built, Ingersoll Labs. And you can see in just a moment as it rotates through up on this side, this is where the heat stop in the secondary mirror is. And where you see this sort of concertina, this is the plate for the primary mirror. There's no mirror on it right now, but you can see this is where it will go. So the light comes in from the sun, bounces off the primary and goes into the heat stop and the secondary, and then back down here and into the rest of the instrument lab. And then these are some still pictures. This is for scale. You can see some people right here, just how tiny they are compared to this. The light comes in here, bounces off the primary mirror, and you can see all these wires on the back. That's because the mirror has actuators on it, so they can actually push and pull on the mirror to compensate for forces of gravity and major turbulence systems that they see in the atmosphere. And then up here we can see again the heat stop and the secondary mirror in this little area here. We have another question.
Yeah, so there's a lot going on in the telescope, and a really great question came up from Brad Denny. He said, "Could you name a profession at the telescope that we would not think would be there?"
Conservational biologist, I think, is one that most people are surprised by. So when they were building the telescope, they wanted to make sure that any animals that were in the vicinity were cared for and treated appropriately, and made sure that their habitats weren't disturbed. So we had a conservationist on our staff for a little while. We have so many different jobs, people with different jobs at the telescope. We actually have some materials on this on our website that you may want to look up. We have some career cards. We have a career booklet as well, I believe, and we're going to be producing more information about the different jobs, because it really does take a village. There are so many different types of careers that are available to you at a telescope. And I think most people think that you have to be an astronomer to work at a telescope. And actually, I think the number of engineering positions we have vastly outweighs the number of astronomy positions that we have. So that's just something to keep in mind. If there's a telescope near you and you're technically minded or interested in any way, then it's worth considering. Another position that you might not realize would be a science writer. We're actually about to hopefully start hiring a science writer for NSO. So if you know any good science writers, send them our way. And that's, that's a really important part of our work. So we have all different kinds of positions available at the observatory. It's a very cool place to work, I have to say. So one more picture here. This is just a different perspective. So in this case, the sunlight's coming from behind us. This is reflected light over here. This is the primary mirror, this one right here. And so you can see how highly polished it is. This was the concertina that you saw in the video earlier pulled up. This is the protective shield. The light comes in, bounces off the primary mirror and up into the heat stop and into the secondary mirror right here. And you can see all of the pipes for the coolant running through this area of the telescope to make sure that everything stays as steady at temperature as possible. So then Parker Solar Probe and Solar Orbiter, they also fit into this. So I mentioned this earlier, that they're traveling towards the sun. So the Inno Solar Telescope is at Earth, and this teal picture here, or the teal track, I should say, this is the Parker Solar Probe. And you can see it getting closer and closer to the sun. And then this darker green is Solar Orbiter, and you can see it also approaching the sun. So between Parker Solar Probe, Solar Orbiter, and the Inno Solar Telescope, all of these telescopes studying the sun from different perspectives at different distances, we're going to be able to build a picture of understanding of our sun and its behavior like we've never been able to do before. This is truly revolutionary for solar physics and also our place in the sun's atmosphere. We live in the atmosphere of a star. And so it's important for our own well-being that we understand literally what makes it tick, what makes it behave the way it does. So the next decade, well, the Inno Solar Telescope will continue to run for 50 years, but the orbital, the satellite instruments will run for significantly less than that. So the next 10 to 50 years is going to be a really interesting time for solar observations and solar studies. So I hope that you enjoyed this. I'm going to just let this play in the background. It's pretty much just gratuitous pictures of pretty solar flares, and I'm happy to take any more questions that you might have. So if you would like to read me out Alex's question again, Tishana, I'm happy to answer that now.
Sure. Let's see. Actually, let's answer one about solar flares first, since you have that video playing. Yeah. So this is a Facebook comment, and it asks, why are solar flares frequent during the declining phase rather than during solar maximum?
So it's not that they're not common during solar maximum, it's just that we get some of the biggest ones during the declining phase. And the exact reason, I would be remiss to claim I knew exactly why, but my understanding or my theory behind this is the reason that we have the solar cycle is the sun's magnetic field starts like a bar magnet. So it starts pretty north-south facing. And there's a process called differential rotation. And this is the process where the sun and its magnetic field rotate at different speeds. So the equator rotates quite a bit faster than the poles do. And so as a result of this, the magnetic field, which is sort of frozen to the plasma, gets dragged faster at the equator than it does towards the poles. And what this looks like is then two bands of magnetic field underneath the surface of the sun that has gotten wrapped up and wrapped up and wrapped up. And it causes, eventually, there's so much wrapping of the magnetic field, it causes the magnetic field to burst out through the surface. And so then the sun is in this very heightened state of energy. This is really unstable. So if you may know that nature likes to be in the lowest possible energy state. That, you know, having things in really unstable situations tends not to last very long. So this is an unstable situation. So the sun then spends a while trying to unwrap itself. And it does this through this process of solar flares. It's actually called magnetic reconnection. And it's literally where you have a magnetic field line that comes together and sort of touches off itself like a shortening out of a circuit. And when that happens, it releases a bunch of energy. That's our solar flare, the bright light. And often it also releases mass. And this is where coronal mass ejection comes into it. But when it does this, it then gets relaxed. It can go back into a lower energy state. And that process of solar flares happens over and over. So my theory is the reason that we start to see some of the really big ones in the declining phase might be, and again, this is unproven, this is just an idea, might be because there's some like last final wraps that are in there that need to just be dissipated in order to get back to kind of a stable magnetic field. And it's, you know, they're just easier to access because there's not so much wrapping going on at that point in time. I could be completely wrong, but that would be my guess if I had to make one. It's a great question though.
All right, and then back to Alex's question. Claire, he wants to know what you're looking forward to in the next few years in solar research. And also, will the 2024 eclipse be interesting since we'll be in maximum?
So what I'm looking forward to is what the trifecta of the Inno Solar Telescope, Parker Solar Probe, and Solar Orbiter produce together, how they're going to work together and what kind of new discoveries they're going to make. And, you know, part of the brilliance of working in a research area is you kind of don't know what's coming. You know, when Parker Solar Probe was launched, they discovered this concept called switchbacks, which were these trails in the solar wind that nobody had ever seen before. And so finding the things that nobody's ever seen before is really what's exciting. So having these three different observatories working together is something that I'm really excited for. And will the 2024 eclipse be exciting? Yes, I think it really will. So for anybody who doesn't know, there is another total solar eclipse passing across the continental United States in 2024. It's going, excuse me, it will start in South America. It will come up through Mexico and through South Texas and then make its way in a straight line up to New England. And so that will be the cut from Texas to New England. In 2024. There'll also be an annular eclipse in 2023 that will make its way from California across the close to the southern borders, again through Texas and out the East Coast. And the difference between a total eclipse and an annular eclipse is with a total eclipse, the entire surface of the sun is covered and you can see the solar corona. An annular eclipse, because of the distance between the Earth, sun and moon, it's not fixed all the time. The moon actually appears ever so slightly smaller. And so that you can see a tiny sliver of the edge of the sun's disk, the sun's surface around the edge of the moon. So the corona is not the feature in this point, it's the edge of the sun. So they're going to be quite exciting. So of course, during the totality period of a solar eclipse, which is very short, it's about 2 minutes, it's unlikely that you'll see much. If we got really lucky, there might be a coronal mass ejection. That would be spectacular, I think. But in the progress up to totality, we will, if we have sunspots that will look like this, because mid 2025 is when we're expecting there to be the peak of the next solar cycle. And if we have big sunspots and active regions like this, as the moon moves across the sun, it will highlight these regions, and it'll even help us be able to see them in even more detail. So it will certainly be very different to the 2017 eclipse, if anybody saw that. And not only that, but when we see the corona during solar minimum, as I mentioned earlier, is very linear. So it's very well structured. During solar maximum, we have all these loops bursting off the side of the sun, but they're not bursting, but they're sort of sitting. So we'll see loops like this guy here in the corona during the totality period of the eclipses. So thanks for your question, Alex.
So we have another great question. So it's from Brad Denny. He wants to know, do you think we will ultimately decide to harvest energy from the sun compared to other power sources? So that'll be our main.
I think that it is a really good idea. We are already making great inroads into doing that. I personally have solar panels on my house, and I think more and more people are getting solar panels personally for their residences. It's something that, you know, it's still kind of a commitment. It's a hard thing to do if you know, maybe you're not located in the right spot. I'm from Ireland, that's where my accent is from, and having solar panels in Ireland is not nearly as fruitful an endeavor as having them in Colorado. Here we have beautiful clear blue skies. In Ireland we have lots of overcast and rain, and so you just don't get the same levels of sun. So there's a lot of that. I think the cost involved can also be prohibitive for some people. They're kind of a big undertaking. Ultimately they do end up breaking even, but it means that you have to be able to pay for them up front. And so my hope is that as time goes on, that the cost will reduce, it will get lower, and there'll be more incentive for that. But I don't think it will be a one-stop shop. I think solar power on its own won't be enough. I think using other renewable energy sources will also be really important. So wind and wave power and other forms of renewable energies, I hope is the way of the future. Just moving away from petrochemicals in general, I think will be something that we'll need to do for the planet.
Gerard Oribe asks, is it possible to get a PhD or be in touch? So I think he means in this field or possibly working with the Inno Solar Telescope.
Oh, I see. Yes. So yes, it's definitely possible to get a PhD in this topic. I can't give it to you, unfortunately. But we have graduate students that are enrolled at the University of Colorado in Boulder, primarily, who work with the National Solar Observatory in the Boulder offices. We also have some students at the University of Hawaii who work with us in the Hawaii offices. So if you're interested in going to graduate school to study the Inno Solar Telescope, there are two options for you. However, if you are interested, there are many different universities all over the country and all over the world who are using data from the National Solar Observatory, and specifically will be using data from the Inno Solar Telescope. So you don't actually have to be at the National Solar Observatory to be able to use our data. That's the beauty of a federally funded program, is that it's free and open for people to use as they wish. So once operations has settled, and it'll probably be a few years, but at that stage then the data will be, or the telescope will be available for people to apply to time for, and you'll be able to gather your own data even if you're not at NSO. So yes, absolutely, I would strongly encourage you to get a PhD in this topic if it's something that interests you. And if you'd like to get in touch, the easiest way to do so is to email outreach, outreach at nso.edu, or you can email me directly at Claire, CLAIRE, at nso.edu as well. And so we'd be happy to advise if that's something that you're interested in. Any more questions? Shanna?
Yes, we do. There's a lot of interest in this topic. So this is from Brad. He's asking, has there been some scenarios of CME EMP lately? And what do you think about Carrington level events?
So CMEs and EMPs at the government level are treated the same way. So the White House has an emergency plan if we get an EMP, which is an electromagnetic pulse, which is a man-made device for the most part. If anybody's ever seen Ocean's 11, they use one in that movie. Whereas a coronal mass ejection obviously is made by nature, but the impacts on Earth often are considered the same way. So we've had some coronal mass ejections and we've had some solar flares, but not at the level of EMPs. And so that's not something that has had to be a worry yet. The impacts that we worry about with that involve our power grids being overwhelmed. So normally the power grids run at a fairly high capacity. And when you have large magnetic fields like this and large energy sources, it can induce additional electricity in the power grids, which can make the transformers blow. They get overpowered, and that can have an impact on our electricity grids. I think the last known time that happened was in 1989 in Quebec. There may have been a more recent one, but that's the one that jumps to my memory. Another impact that we have is loss of communications. And this is, in my mind, this is a more pressing issue. So during Hurricane Irma in 2017, which was the hurricane to hit the East Coast and Florida in particular, I think, or Bermuda perhaps, there was a simultaneous large solar flare. And so you saw some of the large solar flares earlier on from the 2017 period of time. And what happened there was when you have a large geomagnetic event like this, it can cause changes in the Earth's ionosphere. And that will be a whole separate talk, I think, but it causes changes in the Earth's ionosphere, which is really important for communications, and especially radio communications. And so it meant that the first responders who were doing the hurricane response weren't able to use their normal methods of communication because of the solar flare, the coronal mass ejection happening at the same time. Actually, now that I think about it, I think the first responders were okay, but the ham radio operators who were helping with the rescue efforts were not able to use their tools because they were being impacted by the solar flare happening at the same time. So that impact on communications and GPS and so on are often more effective in our daily life than the likes of a really large EMP. That doesn't mean that we shouldn't be prepared for them. And I think that there's a lot of work currently being done, especially in the White House, on preparations. There's a new bill currently on the House floor that they are hoping to pass this time around that will sort of help with policy and so on in preparation for things like this. So as far as preparation for a Carrington-like event, we have one data point for a Carrington event, and so it's really hard to know exactly what to expect. The solar scientists think that happens about every 150 years statistically. There's a number of things that have to happen in order to make that be an event. There was actually a really large event in 2012 that I might be able to pull up a video for in just a second, that luckily was not pointed towards the Earth. It was pointed directly away from the Earth, so that meant that we were safe. We didn't have to worry about it. But there was a series of coronal mass ejections followed by another really large coronal mass ejection that, had that been directed at Earth, could potentially have had those kinds of ramifications. So again, it's really hard to know. It's high risk, low frequency kind of an event. So I think it's the kind of thing that we need to be prepared for and need to pay close attention to, and make sure that we continue to understand the sun and study these events in order to be able to identify when they're likely to happen as best we possibly can. Let me see if I can pull up that video while Tishana's asking any more questions.
I think we are good on questions. We're coming up on the hour. Okay. Do you want to play the video?
Yeah. So this is not data. This is a simulation by it's called Enlil, and it is run. Let me see, move this down here. So this is from July 2012. So these are two different views. This is the sun in the middle. And in this view, we're looking down on the solar system. So you have the Earth here, Venus and Mercury, Mars, and then stereo A and B are two satellites. And then in this picture, we're looking side on. So if you were able to take a slice through the solar system. So the sun here, the Earth here. So you'd have the planets lined up this direction. So I'll just play this and we can see what happens. So we have these the red and blue and black are coronal mass ejections. So you can see there was 3 together, and then this, that really big one. So there's always discussion and debate within the science community about the effects of things that didn't come to be. But my personal opinion is that this one would have had some pretty specific potential to have some big impacts if it was bound towards the Earth. But you can see how frequent these coronal mass ejections happen, and especially at solar maximum. These are, they happen pretty much, multiple times a day. So this is not something that we need to be worried about. This is par for the course as part of living within the atmosphere of a star, but that doesn't mean that we shouldn't try to understand them as best that we can. So yeah, well, thank you for listening, and I hope that you enjoyed this and got something out of it, and that you go and check out some of our other Learn From Home webinars. We have a playlist on the NSO YouTube page, and I hope you find them useful. And thank you.